Okay, so cardiac action potentials there's two different kinds of cardiac action potentials. There's action potentials in the SA node, and then there's action potentials in contractile cells, so like ventricular cells are contractile cells. And these action potentials look slightly different depending on where you are. So I'm going to start with the SA node. In the SA node, there is no real resting membrane potential. So these cells kind of just go from being hyperpolarized back to starting to be depolarized, hyperpolarized to depolarized, action potential, hyperpolarized, depolarized, action potential, that cycle. This part of the action potential right here is we call it number 4. It's when these channels called HCN channels are open. And these channels are sodium channels. They're voltage-gated sodium channels, and they're like basically the opposite of the sodium channels that we would think would be present in the cell. So they're open when the cell is hyperpolarized. So when the cell hyperpolarized, had to think. So when the cell goes below threshold, that's when these channels are going to open. Because in this cell, because there's no resting membrane potential, we call hyperpolarized anything below threshold. Then, since they're voltage-gated sodium, that's going to kind of depolarize the cell just a little bit, get us to threshold. Once we hit threshold, step 0 is caused by voltage-gated by calcium channels opening. And there are two types of calcium channels. There's T-type and there's L-type. And the T-type open really fast, so they're going to be the ones that open down here at threshold. And then the ones that open like more up here or like maybe even up here are the L-type calcium channels. They're longer lasting and they take longer to open. So they don't open quite nearly as fast. So hence the L-type part. Then step 3 is caused by voltage-gated potassium channels opening. Just like it would in like a skeletal muscle cell, that's what's going to bring things back down to threshold in this case, so we can hyperpolarize. And these voltage-gated potassium channels, they actually take longer to overcome the calcium. So this hill right here is wider. So this is wider because of that. So it takes the voltage-gated potassium channels longer to overcome the T-type and the L-type channels than it does just like the sodium gate. An important note about this HCN channel, we also call it the IF channel. But it is cyclic nucleotide controlled. So we can either stimulate it or like shut it down, basically with cyclic nucleotides. So if we increase cyclic nucleotides, we open more channels. And this would cause the cell to depolarize faster. So we would depolarize faster, shoot up, come down, depolarize faster, shoot up, come down, depolarize faster, causing an increase in heart rate. Right? If we decrease cyclic nucleotides, this also is caused by stimulating the beta-1 receptor. This is caused by stimulating an M2 receptor. Then we actually open what's called a GERK channel. And the GERK channel is a potassium channel. So we slow depolarization, which is going to decrease heart rate. because it would take longer to depolarize, because basically your potassium and sodium are getting in a fight with each other because potassium's flowing out while sodium's flowing into the cell. So your depolarization looks something like that, and then you action potential, and then depolarize, and then action potential. So you slow down. Then in contractile cells, the mechanism is like entirely different. It's really upsetting. Some of the steps are the same, but not really. Step number 4 is caused by IK1 channels being open. And these channels are potassium channels. And they make it so that RMP is basically NERST. So it brings resting membrane potential to like roughly 90 millivolts, which is pretty much NERST potential for potassium. Then 0 is voltage-gated sodium channels are going to open when we hit threshold, or when an action potential comes into the cell. So yeah, when we hit threshold. Step number 1, voltage-gated potassium channels open. And these open, and then they close really fast. And then also calcium-induced chloride channels open. And this will make sense in a minute, because we get calcium from the extracellular space, and we get calcium from inside the cell. So we have an influx of calcium, which causes this. And then in kind of like this area right here, we also are going to open calcium channels. And again, we're going to open T-type and L-type. Then in step 2, we open 3 different channels. So we open IKUR channels, IKR channels, and IKS channels. So IKUR opens first, then IKR, then IKS. All of these are potassium channels. All of them are going to let potassium out of the cell. All of them are in hopes of bringing the cell down to resting membrane potential. All of them are fighting against calcium that's flowing into the cell, hoping and praying we can overcome that calcium influx. As we hit like IKS, we're going to start turning that curve. So as we open more and more potassium channels, that driving force for potassium is going to start overcoming calcium. Then in step 3, we're going to open IK1 channels, because IK1 channels start to open as we're getting more hyperpolarized, just like the HCN channels. So we open IK1 channels as we repolarize the membrane, and the further down in repolarization we go, the more we open. So here there might be 1 open, here there would be maybe 2 or 3 open, and then in step 4 we open all the IK1 channels, which are all open, and then that's why our resting membrane potential is so low. In step 4 we also have potassium leak channels, still just like we would in like skeletal muscle, which again is making the cell super permeable to potassium, hence the really, really low resting membrane potential. Which also is why this right here in step 0, why that is so steep, because the driving force for sodium is like wild. It's way stronger than it is in a skeletal muscle or a nerve, because resting membrane potential so low. Then for how calcium gets like in and out of the cell and the sarcoplasmic reticulum and into the cytoplasm, we have an action potential that's going to flow down a cardiac cell, and it's going to hit a L-type. This is an L-type calcium channel, and it's going to open the channel, and we're going to have an influx of calcium into the cell, which is going to bind to the ryanodine receptor on the sarcoplasmic reticulum. And calcium is going to be released from that too, because our sarcoplasmic reticulum is going to be open. Then that calcium can go bind to sarcomeres. Well, it binds to the troponin. Sorry, my mind went blank. Binds to the troponin on the sarcomeres. That moves the tropomyosin. We have a contraction. Blah blah blah. So that allows for contraction. Then the Circa pump, just like in skeletal muscle, is going to pump, oh my gosh, the calcium back into the sarcoplasmic reticulum. I really labeled this thing wrong. Okay, whatever. This is a sarcoplasmic reticulum. Then, because we got some of the calcium from the extracellular fluid, we also have to pump it back out that way so that we have the right calcium balance. So we're going to pump 1 calcium out and 3 sodiums in. So we're using secondary active transport for that. Pretty simple process there. It's also important to remember that the strength of contraction relies on the amount of calcium released. So if we release more calcium, we have a stronger contraction. If we release less calcium, we have lesser contraction. So we have channels to control contraction so that we don't release too little or too much calcium, so that we have the right strength of contraction so that we don't break our heart. Okay, so for ECGs, how they're created, all of that. I have a few diagrams that I already put here just because it's easier than drawing. But to start, if we have a cell, and we're depolarizing the cell, and we put 2 electrodes, if we put like 2 oppositely charged pads on either side of the cell, we can create a dipole, right? Because we have negative charge here, and then we have positive charge here, which creates a dipole, just like we do in any other cell. But then we can create a vector right here that points from negative to positive. And when that vector points from like a negative sensor, or not a negative sensor, points with a negative tail, which is this part. Oh my gosh, no, don't do that. Points to the negative tail, which is this part right here, to a positive sensor, then we always deflect up. Like this, right? So we deflect upwards, and that's one of the rules of ECGs, is tail of vector charge going to opposite sensor equals deflect up. And then the second rule is the magnitude of separation, basically, or the magnitude of the vector equals the amplitude. And the magnitude of the vector is determined by the separation of charges. So this vector is longer because there's more negative than positive, right? This vector has a greater magnitude, right? So it goes like that. However, it starts to come back down because the separation of charge is actually smaller. So it needs to be closer to like the initial like set point, but it still needs to deflect upwards because we are closer to being fully depolarized or fully repolarized or whatever you want to call it. Then in this last one, we are fully negative outside the cell, fully positive inside the cell. So we go from like resting to resting basically. Or like 0 to 0. However, we still have that amplitude and that wave in the center because we are creating all of these steps in between, like the BC in between, BCD in between. And then for F, this is just illustrating that if we were going to be going from a negative tail to a negative sensor, we get a negative deflection, right? So if you go, same thing, if you were to go from a positive tail to a positive sensor, you'd get a positive deflection. If you were to go from a positive tail to a negative sensor, you'd get a negative, hold on, positive tail to a positive sensor, you'd still get a negative deflection. If you're going to go from a positive tail to a negative sensor, you'd get a positive deflection because it's opposite. In creating an actual ECG in a human, on a human heart, we have these vectors, and these vectors in the heart are what create our different waves that we see on the ECG. So I'm gonna start with the P wave and then just like kind of move through it. So the P wave, obviously we're depolarizing a lot of the atria at a time. And we start with the SA node and we depolarize that. And then we're depolarizing down with this general vector position, right? So we should be deflecting up. And that vector continues, we're depolarizing down. So we continue to increase, and we're gonna hit, when we have about half depolarized, we've hit our tip amplitude, which is about right there. And then we have more than half depolarized because we're depolarizing to the AV node at this point. That's what the P wave is gonna get. We're depolarizing our atria, right? So we're still depolarizing. All of this is the same vector point. But in this third image, we have probably about 3/4 depolarized. So we're going back from the top tip amplitude back down because our separation of charge is smaller because we have more negative or more positive now than we do negative. More negative than positive, sorry. And then when we get here, now all of the outside of the cell is going to be negative. We see a whole bunch of negatives, right? Because here we're just starting negative, and now we have more negatives pointing to a positive sensor. More, we'd see lots of negatives, and now this whole node, or all of the atria are negative. They're all depolarized, positive inside the cell, negative outside the cell. And that creates the P wave. Then when we're creating the QRS complex, this gets a little bit more complicated because this is not the QRS complex. That's the T wave. Apparently I put this in a weird order. Okay. So the QRS complex is down here. And this gets a little bit more complicated because we depolarize first, starting with like the bundle of His, and we initially depolarize leftward because the left side's a little bit thicker, so the signal moves faster to the left than it does to the right. So initially we're going to depolarize pretty much straight left, and then the right side is going to catch up. But as we depolarize to the left, that's what's going to create our Q wave. And that's going to cause that kind of small deflection downward because we have this negative charge pointing to a negative sensor. Because overall, we're pointing negative, right? It's a little bit closer to this sensor than it is to that sensor. So we're pointing negative overall. Then, oh no, this is a mess. We get to the R wave, and we are now depolarizing from endocardium to epicardium. So we have a general vector pointing downwards like this, with negative charges spreading throughout the ventricles, which causes that large deflection upwards. And then the S wave, we have kind of the same thing that happened in the Q wave, but like backwards because it takes a little bit longer for that left side to finish depolarizing. So we have a vector that points a little bit up towards the negative sensor, which causes again a little bit of a deflection downwards. Then once everything gets depolarized and is all negative, we have this leveling out that occurs. And that's what creates that QRS complex that we see in an electrocardiogram. Then, to make the T wave, that's going to be the repolarization of the ventricles. And the T wave, we actually start repolarizing with the epicardium and end repolarization with the endocardium. This is because the endocardium has more, I'm trying to remember, the endocardium has a larger plateau than the epicardium does, so they actually move slower in like the uh, um, through their depolarization and repolarization because their plateau phase that we talked about in contractile is longer in contraction. Um, so we start and our uh, arrow is pointing up. And actually, this vector points up the entire time. And we're starting to see more positives. Well, now there's not really an arrow. We start with positives outside the cell this time because we're repolarizing. So we repolarize the epicardium first, then we repolarize the endocardium, which then creates this T wave here, where you start repolarizing and then we hit amplitude when about half is repolarized, and then when the why did I just forget what it's called? The septum repolarizes, we finish and we flatten back out. Um, and mishaps in how these things happen actually are what cause heart attacks and are what cause these interesting things that we see in um, ECGs during heart attacks. So sometimes we see inverted T waves. This happens when the entire ventricular wall becomes hypoxic. Just like the inner ventricular wall. So like, I'm just gonna draw on this right here. If this part of the wall right here becomes hypoxic and we aren't getting oxygen, this could be a blockage to a blood vessel near the heart. Oftentimes this happens on the left side of the heart because it's a little bit thicker um, than the right side. So it's easier for it to get hypoxic because there's more tissue that the oxygen has to pass through. What happens is the plateau phase that normally is longer in the endocardium actually becomes shorter. So our vector starts to point in the opposite direction. And then we have a positive vector pointing towards a positive sensor, and we see an inverted T wave. So our wave looks something like that instead of that one. And that's like the first sign of what we would call like a heart attack or a blockage in the heart. The next step up would be an N STEMI, um, which just means a non S elevated, ST elevated myocardial infarction, right? So if we had a blood vessel right here, which there are lots of blood vessels here because the blood that the heart uses actually doesn't come from the blood inside the heart, it comes from blood vessels outside the heart. So if we had a blockage in this blood vessel, and I'm gonna say the blockage is somewhere like down here, right? And the capillaries are trying to give oxygen, but we're not really getting oxygen to like here. And so these cells start to not be able to depolarize or repolarize, and so they start like basically they start dying. We see a change in resting membrane potential. So instead of sitting at normal resting membrane potential, these cells have a different resting membrane potential, and um, we see a change in like the actual machine, the actual EKG machine is going to read this differently. And so what would happen is we could read a normal EKG, and then we would see it go up, and we would read it normal again. Gosh, I can't draw, but it'll be something like that. And we see that happening because this wall becomes hypoxic. So this is hypoxic, but nothing else is. There's still oxygen to the rest of the heart, but that wall's becoming hypoxic. And that, if that gets bad enough, can progress to what we call a STEMI, which is when it's ST elevated. And what happens is that actually causes a depression um, in our ECG or EKG, and that causes uh the roller shot look kind of funny, but it causes your EKG to look really funny, kind of something along those lines where your T wave looks really quite odd. I'm trying to your T wave is like elevate your S and T wave are elevated. They're not really like as low as they would normally be because your resting potential is not as low. as it should be. So that was be caused by like a full blockage, um, and by like the whole entire wall of the heart becoming hypoxic. So not only is the epicardium or the endocardium hypoxic, so is the epicardium. Um, and so that causes some great problems, obviously, because that's going to come with chest pain and like a surgeon is going to have to go in and remove the blockage. Otherwise, heart cells could die because they're not repolarizing and depolarizing properly. There's not oxygen, and the heart isn't going to be contracting properly, depending on how large the blockage is or how large the hypoxia is in the wall, which then can cause some really huge issues in the long run. But overall, that's like the main cause that we've talked about of a heart attack and how um that shows up on an electrocardiogram. I wish I had put a picture in of that because it looks a lot better when I'm not drawing it. But that's like the general idea. Okay, so in this part of the essay, we're talking about inotropy and chronotropy. And inotropy is the contractility of the heart. So basically, it's like um, the individual fiber contraction because we can't recruit more muscle fibers throughout the heart. So we're going to try to explain the mechanism for how that works because this all happens through beta 1 receptors. So the beta 1 receptors are going to be stimulated by catecholamines, so dopamine, epinephrine, or norepinephrine. And the beta 1 receptors are going to activate the alpha subunit. The alpha subunit is going to activate adenylyl cyclase, which is going to increase cyclic AMP. I skipped the adenylyl cyclase, but hopefully that makes sense. And then the increase in cyclic AMP can cause one of four things to happen. There are four options, obviously. All of them include phosphorylation. I'm just going to write that as PI because I'm too lazy to write phosphorylation that many times. But we can phosphorylate the L-type calcium channels. We can phosphorylate the ryanodine receptor. We can phosphorylate something called phospholambin. And we can phosphorylate troponin. And in the specific, oh, I was thinking and talking at the same time. And in this specific thing, we're actually phosphorylating troponin I. We also can have an interaction with just the alpha subunit, and it's going to interact with L-type calcium channels. But I'm kind of going to ignore it because it does the exact same thing as if we were to phosphorylate the L-type calcium channels. It just happens with an interaction with the alpha subunit. So the alpha subunit interacting does the exact same thing as if we were to phosphorylate. So I'm going to leave that blank, but that is an effect that happens. It just looks the exact same as a different column. So I don't want to write it twice. Um, so if we phosphorylate these L-type calcium channels, it increases the probability of them being open, which is going to increase calcium influx, which is going to increase our calcium concentration, which then increases contractility, which is inotropy. Contractility, which is inotropy. If we phosphorylate the RYR, it dissociates from, I think it's called calstibin. Um, and dissociates from calstibin. And calcibin is just a protein that holds RYR closed. So this is going to increase the probability of the RYR being open, which then increases the calcium that leaves the sarcoplasmic reticulum, which then increases the concentration of calcium available to bind to actin, or to, well, really to bind to troponin, which then increases contractility. It also increases the plateau phase, which increases contractility, which increases inotropy. So that's an inotropic effect as well. Phospholambin is actually not an inotropic effect. However, it has like an indirect effect on inotropy, so we talk about it. When we phosphorylate phospholambin, we increase the rate of the Circa pump,
Circa. So you increase calcium going back into circa, or back into the sarcoplasmic reticulum, I mean, which increases calcium stores. This also increases relaxation rate because we're pulling calcium into the sarcoplasmic reticulum faster. Um, this is going to decrease duration of contraction. In addition, by increasing these calcium stores right here, we have more calcium that can be released with the next action potential, which will increase um, the concentration of calcium in like this step, which will increase contractility. And that is called a lusitropic effect. And then the last one is when we phosphorylate troponin 1, we release calcium faster from troponin C. So release calcium faster from, I'm gonna call it TC, but troponin C, which then again decreases the duration of contraction because we're gonna increase our relaxation rate because we're releasing calcium faster, which is again a lusitropic effect. Um, So those are inotropic mechanisms. Then chronotropic, there are two ways that we control chronotropy because this is your heart rate. So we can control contractility, but we can also control heart rate. Because inotropy, when we control contractility, we're basically controlling like stroke volume. When we control chronotropy, we're controlling heart rate. So the big thing that we're trying to control between these two is our cardiac output. So when we control heart rate, we can control using beta 1 receptors again. This is going to use the sympathetic nervous system, not the parasympathetic. The beta 1 receptors, there are a couple options that we have. One, we stimulate beta 1 receptors, we're going to increase CAMP. Again, just like above, those same steps, the subunit is going to increase CAMP. And we are going to open HCN channels, which these are sodium channels, if we remember that. Which makes it easier to depolarize the membrane. So we depolarize faster and we increase heart rate. That one's kind of like the easy one. The harder one has to do with actually pKa. So when we increase pKa, our pKa can do two things. It can increase the steepness of slope, and oh, I skipped this a step, realizing. Our pKa is going to increase calcium. Um, and that's coming from kind of like these ideas right here, is this is going to increase calcium, or that this is going to increase calcium, really is the main idea there. So we're going to increase our calcium concentration, which then increases the steepness of slope. Um, for the diagram we had here, where we were drawing this right here, right? So we're going to increase the steepness of slope, and if this is your pulse, your heart rate, and each of those is an action potential, we increase the steepness of slope because this right here is step 0, that's controlled by calcium, so your heart is going to go faster. So we increase heart rate. And then the last one is, oh my gosh, I'm blinking. Um, calcium influx can make threshold more negative. And that also will increase heart rate because you get to threshold easier because it's more negative. So once you hit that, and the calcium channel's open, then, you just go. And then your parasympathetic nervous system also has an effect. But your parasympathetic nervous system obviously is going to slow down your heart. So your muscarinic 2 receptors also have some control here. There are three options that we have with the muscarinic receptors. One is that we can decrease cyclic AMP. So we decrease CAMP, which then is going to close HCN channels, which makes it so we depolarize slower. And then your heart rate decreases. Another one is we open GERK channels. And remember, the GERK channels are calcium, not calcium. Oh my gosh. I always think it's calcium because it's a K. They're potassium channels. So we make the membrane more negative. And potassium's leaving, sodium's coming in because HCN channels are still open, but we're kind of getting in a fight, so we decrease heart rate because the slope is not as steep. So if we were drawing that heart rate diagram, it would look something more like that, right? Each action potential would be a little bit slower. Um, and then the last one is the alpha subunit. Again, is going to decrease cyclic AMP. I don't know why I didn't just write decrease cyclic AMP. And then we decrease calcium. So we're going to decrease the calcium concentration, which then increases threshold. It's kind of like the opposite effects that we had in those beta receptors. So we increase the threshold and then we decrease heart rate because it's harder to get to threshold. So we have to work a little bit longer to get there. That's kind of like the idea for how inotropy and chronotropy work and the mechanisms there. Um, yeah. Okay. So for cardiac cycle, we have two graphs that are important. We have a pressure versus time graph and then a volume versus time graph. And you can combine these and make pressure volume graphs, but I'm going to do it separate just because it's a little bit easier to see the different variables. So if we start with aortic pressure and ventricular pressure right here, if aortic pressure is blue and ventricular pressure is red, aortic pressure starts above ventricular pressure, which means that the aortic pressure, not the aortic, sorry, oh my gosh, I'm gonna lose it. This is atrial pressure. This is ventricular pressure. And since the atrial pressure is higher than the ventricular pressure, the mitral valve or the atrioventricular valve or the whatever you want to call it is going to be closed because the pressure in the atria is higher than the pressure in the ventricles. Um, it's going to be open, I'm sorry. So, as the atria contracts, which we show right here in a pressure change, our pressure is going to follow in the ventricles. Our atria are kind of just gonna like level out and they do a little whoop right there. And then our pressure is going to increase in the ventricles and come back down. This is ventricular contraction. Right here is where the mitral valve closes. Because at this point, the ventricular pressure is higher than the atrial pressure. So now we don't want blood flowing into the ventricles from the atria anymore. So the mitral valve is going to close. This bump right here that's in the atrial pressure, is caused by blood flowing back onto the valve or like expanding the atria. It's called a refractory wave. Um, and it just basically is caused because there's like the blood is rushing. It's like this opposing the momentum. Um, then there's another force or another pressure that is important. It's the aortic pressure. So the aortic pressure is going to kind of be above everything else at the beginning. So when we are in And when we're filling the ventricles, um, the atrial and ventricular pressure are a little bit lower. They're probably about, well, the ventricular pressure is, yeah, definitely lower. It's like 80-ish, right? And then we increase to a higher pressure, like about 120. Um, and we are going to intersect with the atrial pressure. And then the atrial pressure is going to, not the atrial, dang it. Now I'm getting all like lost in my mind. With the aortic pressure, then the aortic pressure is going to follow and then kind of go something like this. Oh, gosh, Brother Shaw's way better at drawing this than I am. So we're gonna intersect, and then the aortic pressure increases behind, and then we go like this, and like that. Um, this right here is where you would assume the aortic valve is going to close the semilunar valve, because that's where the aortic pressure is above the ventricular pressure again. This is where the aortic valve opens. So the aortic valve opens here, and we start to have blood rushing into the aorta from the ventricle during the contraction. All of this right here is called the isovolumetric contraction because the volume is the same because we have two valves closed, but pressure is increasing. I'm gonna keep drawing this out just so that we can see this. This right here is where the mitral valve will open again. All of this is isovolumetric relaxation. It's where the ventricles are relaxing, but the volume is not changing. Um, this right here in the atrial or in the aortic pressure curve is called the dicrotic notch. The dicrotic notch is another refractory wave, or basically what happens is the blood is rushing out into the systemic arteries and out of the ventricles. Then, when we rapidly close the aortic valve, some of that blood turns around basically. So we close the aortic valve. We actually close the aortic valve, oh, like right here. That's what we call the notch. And then this is the wave that we get when some of that blood that overcomes inertia turns around and hits that valve again. So then we have an increase in pressure and then we level out. So there's just two waves that are like the refractory waves, or the waves that are like reflections, basically. Then we have a volume versus time graph, and the volume versus time graph is solely for the ventricle. So we start at like 50 milliliters of volume in the ventricle, and then we slowly increase, and then we have aortic contraction. We get to the top, and then we level out for a minute, and then we decrease ventricular contraction, and then we level out again at 50. This right here is end diastolic volume, EDV, because all of this, like up to like there basically, is just like passive filling. And then this right here is not aortic, atrial contraction. And then this is ventricular contraction, so that's systole. So this is end systolic volume. Yeah. During At the end diastolic volume, that's when you're going to hear the lub sound. Because, or your end diastolic volume, because your, well, mitral valve is going to close. At the end systolic volume, you're going to hear the dub sound because your um semilunar valve is going to close. So in here as well, when the mitral valve closes, you hear the leb sound. When the semilunar valve closes or the aortic valve closes, you hear the dub sound. You also can hear a third sound just from blood rushing back and hitting the heart. You would hear it from like right or from blood rushing back and hitting the ventricles. You would hear it right there. So you would hear like, wait, no, I'm sorry. You wouldn't hear it right there. You hear it from blood rushing into the ventricles. So when blood is filling the ventricles, if it comes in with enough force, you would hear a third heart sound. Sometimes that happens, and that's actually normal. But there are like leaky hearts and leaky valves, and those will cause abnormal heart sounds, and that's how we kind of start to tell when someone's heart is not working properly, and we can kind of start to piece together what is going wrong based on those sounds that are not right. Now I'm just reading the prompt really fast, making sure I did everything. Okay. I think the only thing that I should probably go over better is diastole versus systole. So diastole is when the ventricles are at rest, and systole is when they're not at rest, obviously. So diastole is when the ventricles are filling with blood, um, and there's no contraction. So diastole right here ends with the mitral valves closing, and then ventricular contraction consists of systole is what makes up ventricular contraction. So this whole thing is systole, and this whole thing is diastole. And diastole is a little bit longer than systole. It's actually about twice as long. So it takes up about 2/3 of the cardiac cycle, and then systole takes up 1/3. So obviously I drew this kind of improperly, like I didn't draw it with the right scale, but diastole is going to be, yeah, when the heart is filling with blood, when the ventricles are passively filling, and pressure is pretty similar between the atria and the ventricles. And then systole is going to be when the ventricular pressure shoots up, the aortic valve opens, semilunar, and then it closes and it decreases back down. All of that is contained in systole, and then we go back to diastole when the relaxation happens. So systole actually ends right here with the semilunar valve closing. And that's where we start diastole again when the ventricles are relaxing. Because at that point, our contraction is over and the ventricles are relaxing again.